Next, we will introduce time domain reflectometer. The equipment consists of a test host and a coupler. To red coupler high voltage wires, host power cord. This is the single Q line and double Q line. A sampler, data cable for connecting to computer. Coupler grounding wire. This is all the components of the device. Next, let's take a look at the instrument interface. Cable fault tester. This is the grounding post. This is the signal terminal, connecting single Q line or double Q line. This is the USB port, which can be connected to a computer. This is the 220 volts power cord interface, which has a fuse installed inside. This is the power switch. DC is powered by the internal lithium battery of the device, and AC is powered by an external power cord. The left knob is used to adjust the size of the waveforms when collecting waveforms. On the right is the system operation knob. Rotate to select, press to confirm. Power on. The following demonstration tests. Use a single Q wire and connect the core of the product under test with red pliers. Use black pliers to connect the other end of the test object or the armor grounding terminal. This is our B-phase simulation cabinet. This is our armored grounding terminal. The other end of the single Q line is connected to the host signal terminal, and pay attention to aligning it with the anti-foolproof port. Insert and tighten. Wiring is complete. Click to sampling. Adjust the amplitude knob to make the waveform easy to analyze. Click baseline up and baseline down to adjust the baseline and adjust the entire waveform up or down. Click amplitude changes to adjust the magnification of the overall waveform. After adjusting the waveform, click Cancel Hold. Then we click Auto Analysis. The interface will show the total length of the cable, which is 373.24 meters here. We can also perform manual testing by manually dragging or moving with buttons. When you see the pink square below number 1, you can only move the position of number 1 manually. If you want to switch, click the cursor above. Let's analyze the waveform. The interface now displays an open circuit waveform or a full-length waveform of the cable. The characteristic is that the waveform faces one direction and presents the same polarity. Let's take a look at the short circuit waveform. The polarity of the short circuit waveform is opposite. For example, the initial waveform is upward or downward, indicating that the cable or relative armor is short-circuited. Click on the automatic test, and it shows 481.6 meters, which is the short-circuit waveform. Next, let's talk about the test and wiring method of high-voltage flash-over waveform. First, click on the test mode above and select high-voltage flashover. Then connect the sampler and the double Q line. After the connection is completed, place the sampler next to the ground wire of the pulse generator. Then turn on the pulse generator and click Start Boost. Then click the sampling button, and the screen will enter the test and waveform processing interface. Then adjust the waveform so that it is centered and you can see the peak. After adjustment, click Pause Sampling and remove the double Q line on the device. Then click on Automatic Analysis, or you can manually operate the cursor keys. Here we choose the second gear. After manual adjustment, the display shows 181.24 meters, which is the test and fault distance of the high-voltage flash-over method. Let's talk about the waveform analysis of the high-voltage flash-over method. The waveforms of high-voltage flash-over method and low-voltage pulse method are similar. The difference of high-voltage flashover is that it depends on the turning point of rising or falling before the second phase. The reason for this is that the positive and negative waveforms depend on the sampler. We can demonstrate this again by reinserting the double Q line and then flipping the sampler over, and we'll see the waveform change upwards. In addition, according to the different personal habits of the experimental operators, we need to look at the upward or downward inflection point before the second cycle waveform. The above is the waveform analysis of the high-voltage flash-over method.